Welcome back. In this video, we'll talk about the linear regression model. Previously, we have developed a model for test score production. The test score is a classroom outcome variable that we're interested in. The test score y is equal to the potential outcome y evaluated at the treatment d that this classroom receives, and our treatment was classroom size, and the value of a confounder x. And we consider the PD index as an example for a confounder where the PD index measures the percentage of disadvantaged students at the school. We have imposed some structure on this potential outcome function. Namely, we have assumed that we can write it as m, where m is an unknown function, but that is the same for all classrooms, evaluated at treatment and confounder, plus an error term u. Every classroom can have their own value of test score, classroom size, confounder, and error term u. The m function is shared between classrooms. What do we assume about observability? We assume that y, d, and x can be observed. The error term is unobserved. The function m is unknown. We assume that u is balanced in the following sense. If we average u in any subpopulation characterized by a classroom size equal to lowercase d and a PD index equal to lowercase x, that average will be equal to 0. When this balancing assumption is satisfied, then we say that the error term is exogenous. Under this assumption, the m function has a very particular interpretation. To see this, let's take the average of y over this subpopulation. This will be equal to, and now I will just plug in for y. Instead of y, I will put the right hand side, and these are equal by these equalities. Now note that in this subpopulation, every class has this class size and this PD index. So I can replace the general class size and PD index by these two specific values. This is just the m function evaluated at values lowercase d and lowercase x. This will just be a number. And since it's a fixed number, it's just shifting the average by this amount. This means I can take this out of the average. Now, this here will be equal to 0 by the balancing assumption, and therefore we'll just be left with this. We've now shown that m gives us the population average, or the mean of y for given d and x. A good name for m is therefore to call it the conditional mean function. We can abbreviate this by writing CMF. For reasons that will become apparent soon, we sometimes also call m the regression curve. What we've learned here may help us interpret our identification result for the treatment effect. Here we've written the treatment effect as the difference of two m functions. Now we know that this is the difference between the means of two subpopulations. Therefore, it's not surprising that we estimated the treatment effect by subtracting averages over two subsamples. But there was an issue with this strategy. Do you remember? Yes, that's right. The subsamples that we picked were really small. They consisted only of 3 and 4 observations. That's way too small to be informative about the population. Ideally, we want to use our whole sample and not just these small subsamples to learn about treatment effects. We can do this by making a parametric assumption. And that's what we'll do next. This additional assumption will yield the linear regression model. So far, we have assumed that y is equal to m evaluated at treatment D and confounder x plus an error term. Before introducing the linear regression model, I want to get back to something that I talked about earlier. I said that sometimes we want to control for an additional confounder other than x, and that we can do that by changing the definition of the m function slightly. Let's do this right now. We just add the additional confounder to our m function. There we go. Now the labeling of the confounders is a little asymmetric. I'd rather label them x1 and x2. For reasons that will become apparent later, it's even smarter to label them x2, x3. So we're skipping the subscript 1 for now and start labeling with a 2. All these orange-colored variables are observable. What do they correspond to in our example? Our outcome y is given by the test score. Treatment D is given by the class size. The PD index is our first confounder. Let's call it x2. And cohort size can be another confounder. Let's call it x3. At this point, we have to be a little bit more precise. We're not sure that the PD index is indeed a confounder. At this point, we should consider it a potential confounder. We're adding it to our model to control for it. Therefore, we also call it a control variable. Or sometimes we just call it a control. Now we can finally discuss the linear regression model. For the linear regression model, we make one additional assumption. We assume that we have partial knowledge about M. While we don't pin down M completely, we assume that we roughly know its shape. Such an assumption is called a functional form assumption or a parametric assumption. In particular, we assume that we can write M as follows. M at arbitrary lowercase d, x2 and x3 can be specified as follows. Here the blue Greek letters alpha, gamma and beta are called coefficients, and they stand for fixed but unknown numbers. If we knew these values, then we would know exactly what M looks like. The first number here that doesn't multiply anything and that just shifts the regression curve is called the intercept. A number that multiplies a variable is called a slope coefficient. In the context of a linear regression model, the observable variables on the right-hand side, that is d, x2, and x3, are called the regressors. Slope coefficients multiply regressors. To give an example, maybe our M function looks like this. Here I've retained the plus signs so that the pattern is apparent. In practice, obviously, once we have negative coefficients, we often don't explicitly write out the plus sign. The negative sign here means that subpopulations with larger classes have, on average, lower test scores. keeping everything else equal. Similarly, subpopulations with a larger PD score, that is a higher percentage of disadvantaged students, have on average a lower test score, keeping all other variables equal. Of course, if we knew the numerical values of the coefficients, we would know exactly what the M function is, and then it would be easy to figure out treatment effects. We could figure out the treatment effects by plugging into this formula, which is no big deal if we know what M is. In practice, the numerical value of these coefficients are unknown, and we have to use data to figure them out. It's very easy to compute the ceteris paribus causal effect for the linear model. Adapting our earlier formula, the ceteris paribus treatment effect is given by the M function evaluated at baseline treatment plus 1 and confounders at baseline level minus M function at baseline treatment and baseline confounder levels. Now let's plug in the linear parametric form that we assumed for M. So this here is just the first part. Now for the second part, let's subtract. It's easy to see that the alpha cancels, that the gamma times D cancels. This will also cancel, this will also cancel. The only thing that we'll be left with is gamma times 1. Gamma is obviously the slope coefficient of treatment. And this shows us that slope coefficients immediately translate to treatment effects. Gamma is also called the marginal effect because it gives the additional effect of one more unit. The notion of a marginal change is obviously related to differential calculus, and indeed, if we take the M function and we partially differentiate it with respect to D, we will get exactly gamma. Our functional form assumption restricts the treatment effect in two important ways. Our treatment effect is independent of the level of x2 and x3, and it's also independent of the baseline treatment intensity. We'll discuss this more in the future, and we'll also discuss how we can relax these restrictions within a linear regression model. While the linear regression model is restrictive in some sense, at this point it's not really clear what it biases. Remember, we adapted the parametric assumption to help us use all of the sample instead of just a small subset of it. How does the linear regression model help with our identification problem? Consider the conditional mean function M at baseline confounder values, but arbitrary treatment intensity lowercase d. We can depict how M changes as d varies in a two-way plot. We put d on the x-axis and the conditional mean function on the y-axis. For every step that we take in d direction, that is, for every additional unit of treatment intensity or for every additional student in our class, we change the conditional mean function by gamma. Let's use this example where gamma is negative. This means that the conditional mean function is downward sloping. Now consider our baseline treatment of a class size of 35. We can read of the value of the m function at 35 from this graph. It's right here. If we increase classroom size by 1, we decrease the m function by gamma. Gamma is the treatment effect that we want to learn. From this picture, it's clear that we can learn gamma by comparing classrooms of size 35 to classrooms of size 36. This is what we did previously, and previously this was also the only thing that we could do. But now consider a classroom size of, let's say, 25. Increase classroom size by 1. This will decrease the m function by, that's right, gamma. This means we can also learn gamma by comparing classrooms of size 25 and 26. If you think carefully about it, you realize that there are many other comparisons that we can make and that will allow us to learn gamma. In fact, all variation in treatment intensity is now useful for learning gamma. All of this was, of course, with the x's fixed at their baseline values. We're still not using the whole sample. The next step is realizing that if we fix these x's at any other values, then we will draw a picture that looks very similar. At least we will draw a curve with the same slope. It may be shifted upwards or downwards, but it will have the same slope. And therefore we can use the same argument to again learn gamma, even if we have different axes. This will allow us to use the whole sample to learn gamma. You may be wondering, how do we do this exactly? But that's a topic we look into later. So far, we've looked at the linear regression model in the context of this specific treatment effect model. But beyond that, the linear regression model plays a very important role in econometrics and statistics. For example, the linear regression model is not only used for causal inference, but also for making predictions and for forecasting economic variables. Let's briefly look at the generic linear regression model. In our example, we were looking at m of d, x2 and x3, and m was equal to the conditional expectation of y, where we average over a subpopulation, and to determine the subpopulation, we're looking at everyone's d, x2 and x3. So in our example, this was classroom size, PD index, and cohort size. And you belong to the subpopulation that we are averaging over if your d is equal to this value, and your x2 is equal to this value, and so forth. In our treatment application, this link between the m function and the conditional expectation arose from the balancing assumption. Here's the derivation. In other regression contexts, we may just define the m function to be equal to this conditional expectation. Under our parametric assumption, this conditional expectation is linear. In our treatment application, it was very natural to split up our regressors into two groups: a treatment variable and control variables. In other regression contexts, such a split is not natural, and it makes more sense to just have one group of regressors. In this case, we wouldn't call this D, but rather x1 to have perfect symmetry between all the regressors. Now the coefficients are still named asymmetrically. Let's fix this. We just call the gamma beta 1. Now the alpha is really sticking out. Let's rename the alpha to beta naught. This is the generic form of linear regression, and we'll use it when we talk about properties that hold for all linear regressions. As we've just seen, you're free to change this notation and to adapt it to suit the needs of your specific application. For example, you can rename the coefficients as we've just done. You can also rename the regressors. Here we've used simple symbols for the regressors, which is great because it makes for a very compact notation, but it also makes it very easy to forget what these regressors represent economically. Often we will use more descriptive variable names. Let me demonstrate this in the context of our example. At the same time, I'll also demonstrate how to write down a specific linear regression model that you are considering for your analysis. On the left-hand side, we put the outcome variable, y, except maybe we don't want to call it y, we want to explain what it is. Let's call it test score. Now we put the m function here. But instead of writing m, we'll plug in the linear form here. Beta naught plus beta 1. And now we put our x1 variable. In our case, that was d. But to make it easier to understand what d stands for, let's write class size plus beta 2. And instead of x2, let's write PD index. Finally, x3 is the cohort size. Lastly, we put the error term. Let me make some room first. Now we can add the error term. Now we have rewritten our model for test score production in standard notation for linear regression. You're very likely to see a linear model like this one in a research paper by an empirical economist. Here we have retained the standard naming convention for the coefficients. We don't have to do that. For example, here maybe we want to call the slope coefficient on class size gamma, just to make it more obvious that this is the treatment effect that we want to estimate. Our linear regression model here describes how test scores are produced in the population that we are studying. The beta coefficients are unknown values. The next step in our journey will be to try to estimate these values from data. But this is the topic for another video. Thanks for watching.